Well, thank you. And of course, we're all the best of friends. Do unmute yourself at any time and just chime up. It's totally perfect. And I recognize several names here, so I think I've met some folk before. Thank you for having me come back on this precious Saturday morning. I really am honored, and I really appreciate this. It's been a while since I've been up your way. It's been a long, difficult 2 years, as we all know. So maybe one day I can come visit again and see my friends. But let's have some joyous math together right now. So let me begin by asking a very simple question. People who know me know I always begin this way. Is everyone here today aware that there is an international salute to mathematics? It's an official math salute. Do you know the math salute? No. Okay, the few people I can see are shaking their heads. No. Okay, I think we need to start today by doing the international salute to mathematics together. Watch out, it's somewhat unusual. And it's kind of fun too. If you're willing to share your video so we can all see each other, that'd be great. If you're not comfortable sharing your video, that's fine. But here goes. The salute goes as follows. You need your arms completely free. So if you have a glass of water or a pen or a coffee cup in your hands, no. Arms free, and it goes as follows. Arms out front. Great. All right. Right hand over left hand. That's the hard part. Right hand over left hand. Grand. Then you go palm to palm. Okay, then the salute gets strange. You wiggle your little fingers. Then you wiggle your thumbs. Then you wiggle your little fingers again. And then when you're ready, you just come on back. Whoa, whoa, some people did, but some people are stuck. Oh, should I do it again? Should I try it again? Yeah, the answer has to be yes, of course. Yes, thank you. Yes, I'll do it from a different angle, see if that helps. I think this you can see me still. Okay, arms out front, so you can see my arms out front. Okay, my right hand and my left hand. You can see it really is my right hand and my left hand, so there's no cheating there. Right over left. Okay, palm to palm. Great. Wiggle, and then wiggle again. And then when you're ready, just come on back. What is going on? Oh my goodness. Oh my goodness. Would you like some help? Would you like a hint? Okay, okay. Would you like me to give it away? Would you like me to give the full solution away? Okay, that was okay. I'll help. I will half help. Okay. This might seem like a little gimmick, a little game, but actually there's a very good math lesson here. Because mathematicians have a very simple strategy, which is good for math and good for life, that is so basic, so simple, people forget about it. I've given you a problem, and you know what the answer to the problem is meant to be. So if you've got a math problem and you think you know what the answer should be, what's a good strategy you could try? What do you think? If you know what the answer should be, what could you try?
Following steps.
Following steps. If you don't know what the steps are, that might be tricky. Well, I mean, that would be great. I'm with you. If there were steps to follow, great. But what's a good strategy? If you know what the answer should be, what could you try then maybe?
Work backwards.
I know, work backwards. In fact, it's much easier to do a maze backwards than it is to do it forward. So let's start with the answer, see if we can go backwards, see if that helps. So let's start with the answer. The answer must have been that. We know we end up like this. So let's reverse engineer that and ask ourselves, where did that come from? Well, it must have come from that. Okay, so it must have come from your hands tipped over. Then you can ask yourself, well, where did that come from? Well, my fingers are clasped. It must have come from my fingers being unclasped. Okay, now, right now, if you're really doing it with me, you realize that feels very different from what you're doing. That feels strange. So you now got a clue. So we just started at the end, and we got to a very funny feeling middle position. So now your challenge, can you now start at the beginning and get to that same funny feeling middle position? Now you know what it's meant to feel like. Can you get there from the beginning? So there, I've half helped. I've got us halfway back. Your job now is to start at the beginning and go halfway forward. Something's going on right there, obviously. There's a funny feeling middle position. Wiggle, wiggle, wiggle. Come on back. All right, so here's what we'll do. We have about 15 minutes together. I'll stop a few minutes early for sure. And if this is driving you insane, just let me know and I'll give it away for you at the end of this hour. Does that sound like a deal? Okay, I got a few nods. Deal. Okay, so feel free to ask me about this at the end of the session. You got it. All right. Okay, so today we're talking about weird ways to multiply. So let me first ask a question. I'm going to share my screen. My first question is, can you now see my screen? Can someone give me a nods up or something? It should be like my hands. All right. Yes, thank you. Thank you.
Yes.
So thank you. Perfect. So when I was in school, we had to memorize our multiplication tables. Times tables. We had to go 1, 2, 3, 4, 5. Oh, in my school, we had to go up to the 12 times table, all the way up to 12. 1, 2, 3, 4, 5, all the way down to 12. What's normal in America now? How high are kids meant to memorize their tables at some point in part of the curriculum? Up to the 12 times tables? I'm curious.
For third grade, 12, yes.
12, okay. Third graders are meant to memorize 144 different numbers here. Okay, that's a lot. That's a lot. But I think the 1 times tables is not too bad, but I always got up to 5. And I don't think the 2 times tables are too bad. You get comfortable with doubling numbers pretty quickly. In fact, I'm going to do the 1 times tables this way here and keep doing the 2 times tables this way here. The 3 times tables. Uh-oh, my camera's a little bit out of focus. Camera, don't be naughty on me. No naughty cameras. 3, 6, 9, 12, 15, I think it goes. 12, 15. 4 times tables, 4, 8, 12, 16, 20, 16, 20. 5 times tables, 5, 10, 15, 20, 25. And I'm going to stop there because I claim you only have to actually memorize up to your 5 times tables. If you know that, you are good for everything else. Because here's my first way to multiply. It's going to be strange. Watch out. I'm going to stop sharing my screen because I'm going to show you with my hands. Here's how you can use your hands to get up to the 10 times tables. And then I'll get us up to the 20 times tables. So here's what I'm going to do. Suppose I want to do something like 7 times 8. A closed fist represents 5. That's 5. To make it 7, add 2 more digits. 7. Now I want to get the number 8. A closed fist is 5. To get 8, go 6, 7, 8. All right, so there's 7, there's 8. Each finger up is worth 10. So right now I've got 5 fingers up, so that's 50. And all I have to do is multiply my fingers down. I've got 3 down on this side. I've got 2 down on this side. 3 times 2 is 6. I claim 7 times 8 is 56. Am I right? Is 7 times 8 56? Yes, it is. Let's try 7 times 9. Do it with me. Okay, a closed fist represents 7. It represents 5. So to make it 7, add 2 more digits, 6, 7. To make this 9, closed fist represents 5. To make it 9, what would I have to do?
63.
Okay, it's going to be 63, hopefully. To 9, I put 4 more fingers up. Okay, great. Each finger up is worth 10. Right now, multiply the fingers down. There are 3 down on this side, 1 down on this side. 3 times 1 is 3. I claim 7 times 9 is 63.
Yes.
Like you just said. Whoa, this is crazy. Okay, give me another one up to the 10 times table. Let's do another one together. Someone tell me another one we can try.
Seven times 6.
You bet. 7 times 6. How are we going to do it? Let's try it. How would that one go? 7 times 6. First of all, represent the number 7. Yes, I see that. Then represent number 6. I see that. Okay, each finger up is worth 10. So that's 30 right now. And the only multiplication you actually have to do is the fingers down. Multiply the fingers down. What do you get?
42.
Yeah, 3 times 4 is 12. So 30 and 12 is 42. This is wild. This is wild. Okay, let's go to the other extreme. What's 10 times 10 with this method?
5.
Make this 10. Yes.
10.
Make this 10. Yes. Each finger up is worth 10. That's 100 right there. And nothing to multiply by nothing to multiply. Yep, 100 is the answer. Wow. Okay, are you ready for more? Are you ready for the next level up?
Yes.
Okay, that was fingers. What do we use fingers and toes? Now you can't see my toes, forgive me, I'm wearing like big, thick woolly socks, it's cold down here. But we can now go up to our 20 times tables. So on my right-hand side, all my toes are down, all my fingers are down, that's now worth 10. On my left-hand side, all my fingers are down, all my toes are down, that's also worth 10. If I want to do something like 17 times 18, here goes. On the right-hand side, I'm going to make number 17. Everything down is worth 10. To make it 17, I'm going to put 5 toes up and 2 fingers up. You can't see my toes, but now I've got 7 digits up on my right-hand side. So 10, everything down is 10 plus 5 digits up makes that 17. To make this side 18, currently everything is down, it's worth 10. I'm going to put 5 toes up, which you can't see, and 3 fingers up. All right, so on this side, I've got 7 digits up for 17. On this side, I've got 8 digits up for 18. Now, because I'm using all fingers and toes, every digit up is now worth 20. So I've got 7 things up on this side. I've got 8 things up on this side. I've got 15 things up in total, each worth 20. That's 300 right there. And all I have to do now is multiply the things that are down. 3 down on this side, 2 down that side, 3 times 2 is 6. I claim 17 times 18 is 300, all my fingers and toes, and 6. Is it? Okay. But if I really want the answer, here's what any person in the 21st century would do if you have one of these things. If I can get my Siri. Hey, Siri, what's 17 times 18?
17 times 18 is 306.
Yes, it is. Whoa, whoa. Your turn. What's 19 times 19? Yeah, can't see each other's toes. Everything down is 10. To make it 19, it'll be that, I guess.
361.
361, I heard that, and it sounds good to me. That's what I'm seeing. 18 things up, each now worth 20. 18 times 2 is 36, so 360. 1 times 1 is 1. I bet 19 times 19 is 361. And is it?
Yes.
Whoa! Now, is that a weird way to multiply? Does that really seem weird? Yeah. So I guess our real challenge for today is to figure out why that is working. It seems magical. So if you want to just go up to your 10 times table, just use 10 things. So something like, 9 times 8. Remember, if we're just doing up to 10 times tables, everything's worth 10, so that's 70. 1 times 2 is 2, 72. If we go up to 20 times tables, use fingers and toes. And that's very impressive then. That's great. All right, so there's our first mystery for today.
So, James, you
Yes.
did big numbers. Can you do 3 times 2 with a 20 and explain how that works?
Well, I think you just need to know up to 5 times tables. So 3 times 2. I claim you need to know that one. Yep. There are some, you need to know your small ones. But once you know your small ones, then you build up to bigger ones. But that's a good question. What if I start mixing big and small numbers together and do those multiplications as well? All right, that's our first mystery for today. But I'm going to just present a couple of mysteries. Here comes a second mystery, a brand new mystery, another weird way to multiply. So here is a beautiful visual way. I'm going to share my screen, my paper. I think my camera's going to behave today. All right. Suppose I want to do something like 21 times 32. There, I'm on camera. Here is a very weird way to do it. I don't recommend it. I'm just saying it's a weird way to do it. The number 21, I'm going to represent it with lines. I'm going to do 2 vertical lines for the digit 2 and 1 vertical line for the digit 1. There is 21, 2, 1. For 32, I'm going to see the digit 3, I see the digit 2. I'm going to do 3 horizontal lines for 3 and 2 horizontal lines for 2. All right. Then I'm going to count intersection points. There's a little cluster of intersection points right there. There's 6 of them right there. And there's a cluster of intersection points right, there's 3 of them right there. And there's 4 intersection points right there. And there's just 2 intersection points right there. And now I'm going to be extra weird, and I am going to add up these intersection points diagonally. One cluster there is 6 of them. This cluster makes 7 of them, and that cluster makes 2 of them. I add them up diagonally. I claim 21 times 32 is 672. Whoa, whoa. Let's see, is that right? Is that right? 21 times 32, 672. That's weird. That's weird. All right, your turn. Your turn. Do you have paper and pencil with you? Try 331 times 12. Try doing a 3-digit number times a 2-digit number with this line method. Each digit represented by some lines and some horizontal lines, vertical lines and horizontal lines. 331 times 12. Try it on a piece of paper. And I'll do it too, if you watch me.
Three, 9, 7, 2.
Oh, is it? I don't know. Can someone agree? Does someone confirm that?
Yes.
Yes, 3972. And is it true?
Yes.
It really is that? Okay. I'm in the 21st century, so I'm going to do my 21st century thing. Oh, whoops. 331 times 12 is 3972. Indeed it is. This is weird. This is weird. Let's do another one. I'm having fun. Try 341 times 12. See if something strange happens there for us. Oh, no, let's make it bigger. Let's make it 23. Sorry, let's make it really strange. 23. Give me. And the answer is going to be 341 times 23. Apparently, that's what the answer is going to be. So I don't care about the answer, actually. Just this weird method. It's more interesting than the answer. So I'm wondering if there's a little issue with this one.
The double digit.
Oh, a double digit. Yeah. So what answers is this method giving? I mean, it's going to be a little bit strange, I suspect. So 3, 4, 1, 2, 3. I am seeing 6. I'm seeing, oh, what's that? 12 and 9. Is that 21? Is that right? And I'm seeing 2 and, oh, golly gee, 8 makes 10. Oh my gosh, double digits all over the place. And 3. So I'm getting the answer 6, 21, 10, and 3, which doesn't look anything like that to me. Did I do that correctly?
You need to regroup.
Oh, 8. Oh, sorry, did I do that correctly? Actually, that's 8 of them there. That's 9 of them. 8 and 9. 17. Forgive me, it's 17. Oh, regroup. Oh, regroup. Okay, so if I regroup, because what you're telling me, I think, is 10. What have I done? Can I count? Can I count today?
The third is 14.
The third one's 14. Is that better? Because I can't do basic arithmetic.
I guess.
12. Oh, 12 and 2 is
Plus 2,
14.
14.
Oh, golly gee. You have me come along tomorrow and you can't actually multiply. Turns out I can't count. All right. So 6, 17, 14, 3 is what the method's telling me if I can actually count my intersection points, which I can't. And people tell me regroup because what 14 tens you're telling me is really the same as 4 tens and 100. So the answer is really 6, 18, 4, and 3 if you regroup. Is that what you meant by regrouping? Okay, I've got some nods. That 18 is a bit weird. Oh no. Is there more?
Oh, can I explain?
Yes, please help me out.
Okay. Okay. This is Mirna of Rock Point Community School. And
Oh, hello.
I noticed, yeah, you have 6, 17, 14, and 3.
Okay,
So
6,
the
17,
10,
14.
yeah. So the 10, so you have to remain 4 for the third digit. And then the 1 you have to add to 7, so it will become 8. And then
Okay.
the 10 from 17, you have to add to 6, so it will become 7.
Okay.
So you have
I think I know exactly what you're doing. So you got the 1s, the 10s, the 100s, and the 1000s. I'm doing a place value chart. I got 6,000s. I got 17, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 5, 6, 7, 1700s, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 1, 2, 3, 4, 14 10s and 3 1s. That's what we've got right now, which is crazy. Except you just told me 10 of these are really 10 10s is really the same as one of those. So I've now got 4 there and now I've got 18 there. But then you also just said, I heard you say 10 of these, 10 100s is really 1000s. That means I've got 8 there and 7 there. That's what I heard you say. Is that group exactly the way you just described? That is beautiful. There we are. Yes. So my method was working. It was just a recording start again. All right. 102 times 310. Try that one with this method. And just so we know what the answer is meant to be, 102 times 310 is this answer. We're meant to get 31,620, but I want to see if our method gives that. So I'm curious what sort of challenges or struggles or issues might be in your minds for this one. What are people thinking and experiencing and feeling right now?
How do you represent the 0?
That 0 is annoying. I'm with you. Okay, so someone's confirmed it's 31,620, but how do you deal with the void? Yes, I like that way, the void. It gets crazy with the void. Sounds like some people had success. How did people deal with the void? What did people do for the void?
Just leave that as 0.
Just leave it as a 0. Okay, so 1 I can do. Then I want to do 0. Maybe leave it as a 0. Maybe for my mind, I might just do like a very faint dotted line, though it's not really there. Just leave it as a 0 and then 2. All right, I left it as 0. And then 3, 1, 0. 3 I can do. 1 I can do, and then 3, 1, 0. And then I don't want to do anything there, so I might as well just like leave it there. Okay, I left this voids as zeros. Does it work out now? I add up these things diagonally. Oh, ha, ha. Beautiful. Now, of course, you just see me unable to count, so I'm going to make mistakes. Let's check. 1, 2, 1, 2, 3. 3 intersection points there. Oh, technically, no. There's nothing going on there. That's a void. So there's nothing there and 1 there. So that's a 1. Okay. There are 6 there. There's nothing there. And there's also nothing there. Because nothing's happening there. So that's also 6. There are 2 there. Nothing there, so it's just 2, and there's nothing there. There's no line there, so there's no intersections there, so that's 0. Ha 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 ha. That was brilliant. I like that. Well done. So yes, you can handle these zeros. They are annoying, but if you just really kept track of the void, you're actually okay. Wow. Okay, so the 2 issues are you might have to do some regrouping and you might have to deal with voids, but if you're willing to do that, it looks like this is working. So now the question is, why? It's just like the finger multiplication. Why? But here comes my 3rd way. I'm going to do another way of weird multiplications. I call this weird multiplication school mathematics. Suppose I want to do 37 times 23. I'm going to tell you my honest story as a kid. When I was in school back in grade, I don't know when we were doing this, grade 4, grade 3, grade 5, I can't remember when we did long multiplication. Here's why I think what I was taught in school is weird. I was being taught back in Australia that everything I did, I had to read left to right. I was reading left to right. In English class, we were reading left to right. In history class, we wrote left to right. In social studies, we wrote left to right. Except in math class, sorry, my camera's being really naughty today. In math class, they said, no, James, you don't go left to right, you go right to left. I thought that was strange. That's my weirdness number 1. Then here comes my weirdness number 2. As a child, I had to go 3 times 7, start on the right. 3 times 7 is 21. And I said, okay, it's 21. No, James, you don't write 21. You just write a 1 and put a little 2 up there. I think that's weird. That's my weirdness number 2. Then you go 3 times 3 is 9. So I'm about to write 9. I say, no, James, don't forget about the little 2 there. You can write 11 now. You weren't allowed to write 21 before, but now you are allowed to write 11 all of a sudden. That's my 3rd weirdness. I think that's weird. 3 things. I'm not being honest. I was like 10 years old. This is weird. Here comes the 4th weirdness. Just put a 0 there. Why not? Just put a 0 there. Now go 2 times 7 is 14. And I'm wondering, am I allowed to write 14 or am I not allowed to write 14? No, James, you're not allowed to write 14. You just write a 4 and put a 1 there. Except you should have crossed out that 2 earlier. This is weird. And then you go 2 times 3 is 6. Okay, I'm about to write 6. No, James, don't forget about your 1. Make it 7. This is weird. I have no idea how grade school teachers are meant to teach this to kids in a way that makes sense, because it's weird. Okay, but here comes weirdness number 5, I think I'm up to now. We're doing a multiplication problem. We say, no, just do addition. Turn to addition. And then I'm about to go 7 plus 1 is 8, 1 plus 4 is 5, 1 plus 0 is 1. But no, James, you go right to left in math. You want to go 1 plus 0 is 1, 1 plus 4 is 5, 1 plus 7 is 8. Apparently the answer is 851. It's very hard for us adults to see how weird that is, because we are so used to it. We've been doing this for like, 10, 20, 30, 40, for me, like 50 years of my life, we forget how weird that is. But seeing that for the very first time is weird. That is strange. And in fact, look at this. If I switch the order of the products around, is it obvious I'll get the same answer? Is it obvious I'll get the same answer? And we always say, sure, you can do multiplication any order you like, but look at the long multiplication algorithm. 3 times 7 is 21. Don't write 21. 2 times 7 is 14. Add the 2. Now write 16. It looks very different from what I did before. Write a 0. 3 times 3 is 9. Just write 9. 3 times 2 is 6. Just write 6. Add them up. 1, 5, 8. Whoa, whoa. It gave me the same answer, which I have to say, whoa. Because look at this middle stuff. Totally different. It's amazing, got totally different middle stuff, yet it gave me the same answer in the end. This is weird. I can't understate how weird what we teach kids is. All right, I've now given you 3 weird ways to multiply. We've done our weird finger multiplication. Here's 7 times 8. We've done our weird line multiplication. And I've given the third way that we adults forget is weird, but it really is weird. That is strange. So our challenge together in the remaining 22 minutes of the day, leaving a couple of minutes to do the math salute if you like, is try to make sense of these 3 weird ways to multiply. Does anyone think, oh, easy magic multiplication? Wow. What's it, Marge, what do you mean by the easy multiplication? What were you thinking there? Which part was easy? I'm just looking at the chat all of a sudden. Or do people mean this is the easy method, the standard method? Is that the easy way? Because I think it's very hard, actually. When you're used to it, it feels easy. When you're not used to it, it's very strange.
I think she was referring to the other method with the lines.
Maybe. I like the lines method. I think it's visually beautiful. It connects with so much beautiful artistry and work that we do in our lives. Also, it kind of starts to make more sense. I feel like I own it. This one here is just so removed from whatever it was trying to do that we've lost sight of what it's actually trying to do. It just becomes so abstractified, we can't see what the story is in that anymore. All right, okay, so let's do it. Let's look at multiplication. Example, 3 times 4. I mean, we could say that's just 3 groups of 4. If you want to think of like really sort of basic terms, like here's one group of 4. Here's another group of 4. Here's a third group of 4. And bingo, that's 12 dots. 3 groups of 4 is 12. Yep, that's good and grand. What about 4 times 3? How does that read in like if I'm doing very, very elementary multiplication? It's not 3 groups of 4 anymore. How would I read that now?
Four groups of 3.
Yeah, and that is actually physically different. 4 groups of 3 would be this picture. There's one group of 3. Here's another group of 3. Here's a third group of 3. And here's a fourth group of 3. And it's amazing. You get 12 again. Whoa, they have the same answer. The pictures are very different, yet they give the same answer. Is it obvious why they give the same answer? Why should 4 groups of 3 and 3 groups of 4 give the same answer in the end? They are definitely the same number of dots. However, if I asked you instead about nice numbers, 137 groups of 257 versus 257 groups of 137, I have no idea how many dots there are. It's obvious at the same number of dots. You know, I chose nice numbers for us. If I chose horrible numbers for us, this question gets harder. Is there a general reason why you get the same answer, why they have to be the same number of dots? I'm with you, they are the same number of dots. Is there sort of a lovely reason why they have to be the same number of dots? The groupings are the same numbers. Well, yeah, okay. If we do it this way, let's group them in a nice way. Here's one group of 4. Here's a second group of 4. Here's a third group of 4. So my camera is not showing them to you in a nice focus. Oh, I'm so sorry, I've got a naughty camera today. So right there, I've just drawn a picture of 3 groups of 4 for you. And there are the 12 dots. And I was asking about 4 groups of 3. I was asking the other way around. Now, William's right. They are the same number of dots, the same groupings, but does this picture, if I'm a little more systematic, can you see 4 groups of 3 in that very same picture? How? How are you seeing this? Seeing it? Yes. Yes. Or even just, maybe since I've got my picture on the page here, if I just look this way instead, or rotate my perspective, either turn the rectangle around or just turn my perspective around. Yes, if I look this way, 3 groups of 4. If I look this way, 4 groups of 3. Yes, and either way, it's got to be 12 dots. You're right, it's the same groupings in the end. You're absolutely right. But yes, change vertical to horizontal, or if I want to do, turn the picture around, either way. This is why a lot of people like area, because I couldn't say doing dots, I could do pictures of area. There's another way I could have drawn this picture. Instead of doing dots, do squares. There's 3 groups of 4 squares, and that way is 4 groups of 3 squares. Either way. So a lot of people like area when they think of multiplication. I was counting dots, but people like the area model. In fact, I like the area model too. Suppose I asked you, what is the area of a 37 by 23 rectangle? And my answer would be, ick. That's a horrible, horrible problem to work out. That'd be a horrible problem to work out. I mean, the numbers, I think we even did the numbers today, but that's not fun. So here's a lovely opportunity to teach our fabulous kiddos how to think like mathematicians. And one strategy is, if you don't like numbers that are given to you, can we make the numbers easier? Can we work to avoid hard work? Could I make 37 be simpler in my life? What's an easier version of 37? Anyone got an idea to make the number 37 a bit easier? Yes, please make 37 easier. I could chop up the rectangle. I could make that 30 and 7. That seems a bit easier. And I could work out the area of that rectangle and then add the area of that rectangle. Yes, yes, absolutely right. Okay, could I make 23 easier? Because I don't like hard work. I'm a mathematician. Mathematicians don't like hard work. What can I do to 23 to make it easier in my life? Yeah, Janelle, you're absolutely right. Yeah, 20 and 3 seems easier. 20 and 3. Oh, so now I think I've got 4 little easier rectangles to work with. So let's work them out. So here's a 7 by 20 rectangle. It's basically 14 with extra 0. That must be area 140. Great. 30 and 3. This is a 30. Sorry, this is a 30 by 3 rectangle right here. That must be area 90. This 3 by 7. That must be area 21. Oh, I like this. And this 30 by 20. That must be area 600. And look, the area must be 600 plus 140 plus 90 plus 21, which I think is, what is it? My calculator. 600 plus 140 is 740 plus 90 plus 21 is 851. 851, which is beautiful because, why is that beautiful? Because that is something we did earlier, which I've lost my piece of paper. Oh no, where's my piece of paper gone? I had a good piece of paper with this on it. Oh yeah, there it is, there it is. 37 by 23 is 851. Whoa, whoa. In fact, this is why I like the long multiplication algorithm, how it originally was done. If I did 37 by 23 in a school way, here's what I'm going to do. 3 times 7, I'm going to write 21. Because look, there it is. There's 21. I'm going to write it.
And the width of the rectangle. Forgiven
If I did 3 times 3, but this 3 is not really 3. Oh, we've got someone watching a video. That 3 there is really 30, isn't it? So this is really 3 times 30 is 90. I'm going to write 90. And the reason I'm going to write 90, because it actually is there. There it is. What other parts can I do? There's 2 times 7. Well, it's really 20 times 7. I'm going to write 140 because there it is. It really is there. And this 2 times 3 was not really 2 times 3. It's really 20 times 30. It's really this 20 times 30. It's really 600. I'm going to write 600. There it is. And here's the reason I'm going to add them up, because I chopped up my rectangle to 4 pieces. I need to add up the areas, and I get 851. There it is. There it is. And guess what? That's exactly what the long multiplication algorithm was doing. So I've lost it already again. Where did that page go? Oh, here it is. Look at that. Here's what we did and what I was taught in school. Do you see that this 1, 1, 1 right here is really those 2 pieces added together already? And this 740 here is really those 2 pieces added together already. Here's the thing. This long algorithm method was invented in the 1700s, 1700s, when paper and ink were precious. People did not want to do all this work because that wasted a lot of ink and a lot of paper. They said, can we make the algorithm more and more efficient so you use less and less ink? The less ink you use, it was better 300 years ago. So people said, no, 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 we won't do this long method. We'll start adding parts of this together so we use less ink and get our answers that way. But I think nowadays in the curriculum, they actually do teach this. I think they call it partial products or something like that. But what it really is just chopping up a rectangle. I say, have kids chop up a rectangle. It makes sense for the long standard algorithm. So this weird method that I was taught in school is actually just the area model in disguise. It's just the area model in disguise. Okay, we're getting somewhere. We've got 12 minutes left together in our lives for this part 1. Can we make sense of line multiplication? What is line multiplication doing? What is this one? Why is that working? 341 times 23. So that was a hard one. Let me do an easier one. Let's do 331 times 12. They had none of the problems in it. Can you guys draw me an area model for this one? If you did this by the area model, what would you get? You say to yourself, I want a rectangle, 331 by 12. I want its area, but those numbers are horrible. What would you naturally do to make the numbers easier for yourself if you did the area model on that? Yes, 331, I would do 330 and 1. I'm so with you. And 12 I'll do is 10 and 2. All right, I would do that. So I'm not drawing to scale, but there's 300, there's 30, there's 1, here's 10 and 2. All right, can you fill in the numbers for me? Okay, someone's got them. Wow. Yeah, there's going to be a 3,000 piece. There's going to be a 300 piece. There's going to be a 10 piece. There's going to be a 600 piece. There's going to be a, was that 60 piece? And there's going to be a 2 piece. Okay. Look what happens. What's beautiful if you add these up diagonally. You add these up diagonally, what do you get? Yeah, you get 3,000 from the 3,000. So you add up all the thousands, you get 3,000. Add up all the hundreds, you get 900. Add up all the tens, you get 70. And add up all the units, you get 2. 3,972. So my handwriting is getting a little bit scrawly here. Yeah, that's a bit messy, but look at what's down below. What's the line method doing? It's actually doing the same thing. There are 3 intersection points there. There are 3 intersection points there. There's 1 intersection point there. There's 6 there, 6 there, and 2 there, which are the same numbers we've got here, 3, 3, 1, 6, 6, 2, except the line method just doesn't say keep track of your zeros. It doesn't say really think of that as 300, really think of that as 30, really think of that as 10. It just lets go of the zeros, but really that 3 was 300. So this intersection points is really 300 times 10. It's really 3,000. There's the multiplication we did, but it's really now in the thousands. This one's really in the hundreds. This one's really in the hundreds. This one's really in the tens. That one's really in the tens. That one's really in the units. Line multiplication is doing exactly the same thing as the area model. It just says, you know what? You don't actually need to keep track of the zeros. We can just do that for you automatically. It'll be the same work. So line multiplication is just the area model in disguise as well. Yeah, it's just chunking the sections together, as Dwayne says. Absolutely right. It's chunking all the thousands together. It's chunking all the tens together, all the hundreds together. It's kind of lovely. It's actually doing what someone earlier said. It's doing all the grouping for you. It's just doing the grouping. Now, sometimes you get too much grouping. You have to regroup some more, but it's doing the grouping for you, which is lovely. So maybe chunking is a better word, actually. Love it. Whoa, weird multiplication. This is great. So that leaves us, time is getting short, 7 minutes to figure out the final one. Finger multiplication. 7 times 8 was 56. Why does that one work? Whoa, having explained that one. So here's the number 8. Here's my attempt at drawing the number 8. Here's my attempt at drawing the number 7. There's 7. So what this really is, it's really 5 plus an extra 3 fingers up. And this is really 5 plus an extra 2 fingers up. So that's 7 times 8. So what I'm really is telling you is that 5 plus those 3 fingers up times 5 plus those 2 fingers up equals, so here's the method, question mark, question mark. What did I say we had to do? Each finger up is worth 10. So how many fingers are up? 3 fingers up and 2 fingers up. So it's 30 plus 20, because each is worth 10, plus multiply the fingers down. Fingers down. So how many are down here? So it's 2 down, and this is 3 down. Oh, there's lots of 2s and 3s and 5s here. And multiply the fingers down, plus 2 times 3. So it's correct, it is 56. But why? Was that just luck? Is it always going to work? Is it always going to work? So the answer is yes, it's true, but was it just get luck? It's like magic right now. So I guess the thing that you do, so actually this is now getting to a realm for like middle schoolers and high schoolers. Actually, I think algebra might be the way to do this. I know I'm drawing 3 fingers there, but let's say it's A fingers up. And over here, let's say it's B fingers up. Sorry, my handwriting's getting atrocious with a bad marker. So that means I'm trying to work out the number 5 plus A. For example, it was before 5 plus 3. Now it's going to be 5 plus A times 5 plus B. And I'm hoping that will equal, okay, so what would it be? Each finger up is worth 10. So there's A fingers up, that's 10 A's. And the B fingers up over here, that's 10 B's or B10s. Plus, what's the final thing we have to do? What's the method? Is it A times B, or is it, it's the fingers down, I think it was, they get multiplied, almost A times B. Oh, we need a formula for the fingers down. How many are down here? What's a formula for it? If A are up, you have 5 fingers, yeah, multiply the fingers down. Yes, multiply the fingers down. So there's A fingers up and I've got 5 fingers. How many are down? Yeah, the rest of them, 5 minus A are down. And over here, the down must be 5 minus B. So yes, you have to multiply the fingers down, 5 minus A times 5 minus B. So here's the question then. This is now for high school kids or upper middle school kids. Is this true in algebra? We know it worked for 2 and 3. We had 3 fingers up and 2 fingers up and it happened to work. Is it working in general? Work in general? So depending on your level of comfort with algebra, or question mark, maybe we're onto something. Maybe that will do it. Okay, I'm gonna have to stop there because time is running out at a fierce rate. Time is clicking faster. Don't we need to add some more fingers? Or is that the formula, or did I miss some part of the formula? What do you think, William? Figures. The 10. I've got A10s and B10s. Let's check. Okay, I'm doing 3 and 2, literally. That's 8, that's 7. All right, 5 plus 3 is 7. I'm doing a concrete example. 5 plus 3 is 8, sorry. Times 5 plus 2 is 7. Let's see, each finger up is worth 10. 3 up, oh, A is 3, would be 30. 2 up, B was 2, that would be 20. I've got the 5 up, there we go. And multiply the fingers down. 2 on this side, 5 take away 3 is indeed 2. 5 take away 3 is indeed 3. This 5 take away 3 is indeed 2 is indeed 3. 56. I think we got it. Yep, I think we got it. That is doing the correct thing. So now the question is that a true formula in algebra in general? Because if it is, oh, and Marge says yes. Marge is saying yes, it is. Thumbs up. There it is. There it is. Whoa. That's 3 weird ways to multiply. I claim the school way is weird, but it's not weird as soon as you see it's the area method. Well, I've lost my picture of the area method. Uh-oh. It's really the area method. And once you see it's the area method, you have fun with the line method. And if you're comfortable with the algebra, you actually also have fun with the finger multiplication method. It's kind of cool to get up to a 10 times table. And if you want a challenge for today, remember I did fingers and toes. So what's the 20 version of this to get up to the 20 times table? There must be another algebra formula for that one, which is probably true as well. Okay, I'm going to stop sharing my screen now and say thank you for spending this first hour of this Saturday morning with me. I am truly wowed and awed and honored and so appreciative. So I will stop there, and if you have any quick questions or thoughts you want to share, I'm happy to chat, and we'll go from there. Oh, applause to you guys, You guys are awesome. So thank you.
You did start like 3 minutes after, so. Yeah,
Okay, I'm on mark then. I'm on mark.
certainly love to see questions, and so are there questions for Jim?
Of course, there are many other weird ways to multiply as well. The list can keep going on. So if you want me to go on for another 3 hours, I'm happy to.
I just had a question in there.
Yeah.
Thank you very much for showing me those strategies. But in some of the assessment that kids take, usually it would be not just finding the product, but it would be finding the factors. Is there
Right.
a method?
How do you find the factors of numbers? So that would actually be getting more into division. So the question is, are there clever, weird ways to divide? So I would say what I've done today probably is not very helpful in that regard. I've given you the factors first, find the product. Now you're asking to reverse that process. Given a product, can you find the factors? That's another ball game, I'm afraid. And of course, let me be very clear. I don't think anyone in their right mind would expect students to actually do that every time they multiply. So I'm not saying this is a useful strategy for practical use. However, for really cementing understanding, it actually is worthwhile, in my experience as a teacher, to do these weird things with students, just to really expand conceptual understanding of multiplication. Not because it's a strategy to actually use, but it's a lovely pedagogical tool to enhance understanding. You know, here's something weird. Can we figure out why it works? And if kids can figure out why it works, that means that understanding of multiplication is really quite deep and good. And I say yes to that. So sadly, I can't see how to reverse this easily, though there are good ways to do the area model backwards, to actually do division and find factors, which means there are actually clever ways to do that method backwards and do division and find factors. And there are clever ways to do other things backwards, which could help. Okay, so there we go. Where did I learn math in school? Oh, okay. So my schooling back in Australia some 40 years ago, 40, 50 years ago, was really not very enlightened. It was actually not joyful at all. We were sitting in rows, all facing forward, and my job as a kid was just to memorize and do. So when I was taught how to multiply, I was taught this with no understanding. Here's what you do. You first of all multiply the numbers on the right. If it's too big, you don't write the full number. It was just purely procedural. I had zero understanding of that. So it wasn't until my adult life, when I went back and thought about maths for the first time really in my life, that I started making sense of this for myself and realized actually it's just the area model. It's just like I'm just chopping up a rectangle and just compactifying it. Yes, I am from Australia. I'm from Australia, but I've been in this country for 33 years, living in Arizona now. I live in Phoenix. But yes, so it's just this is more my adult journey with maths, trying to figure out what on earth happened in my schoolhood journey, because my schooling in maths was not joyful and did not make sense to me. I was also deemed good at maths, which I thought was ironic, because I knew I was just filling out my worksheets to please my teacher, not for understanding. I realized my strategy was to please my teacher. So as a 10-year-old, I was cognizant of that. I was not doing this for my own sake. I was doing this for my teacher's sake. And I got my gold stars, my 10 out of 10s, but I knew I didn't understand it. I was just performing and I knew it. So things are much better nowadays. Thanks to you, things are way better nowadays. This is all about let it be a proper human, joyful experience full of understanding, and let maths be a human experience. You know what? And I also love this line method, because I mentioned earlier, just the geometry and the patterns, it feels like it's almost artistic to me. So we can talk about the full experience of the artistry of things like this. It's just, you know, this lovely opportunity to let maths be a beautiful human experience, not just let's get answers for an exam.